In the vastness of interstellar space, an enigmatic object, 3I Atlas, challenges our understanding. Captured by NASA's Mars Reconnaissance Orbiter in 2025, the object exhibits a baffling plume extending perpendicular to the Sun, defying known cometary behavior. Stretching over 500,000 kilometers, the plume contains titanium and chromium, elements rare in natural cosmic phenomena, but integral to advanced materials engineering. 3I Atlas, Anine. Interstellar traveller may have journeyed for eons. Its trajectory and plume suggest it is not a comet, but something potentially artificial, hinting at an intelligence beyond our own. This discovery offers the first tangible clue in the decades-long search for extraterrestrial intelligence, sparking global collaboration as over 50 countries unite to decipher its secrets. Observation. The plume's trajectory defies natural explanation, implying AA. Propulsive mechanism, yet no energy source or exhaust is detected, intensifying the mystery. Interpretation. If not driven by solar wind or thermal processes, the plume must originate internally, suggesting technological sophistication far beyond human capability. Such control over material release would require advanced physics and engineering. Speculation. Could the plume be an intentional signal or a byproduct of advanced propulsion? If a form of communication, it raises profound questions about interstellar dialogue across unimaginable distances. As data continues to stream in, the scientific community braces for a paradigm shift. 3I Atlas stands alone, challenging our understanding of comets and technology. For the first time, we are poised to redefine our cosmic perspective, as the plume of 3I Atlas urges us to question further and push the limits of human knowledge. Standing on the edge of something humanity was never meant to find. If that idea gives you chills, you're exactly where you're supposed to be. Hit like, subscribe, and drop a comment with your theory. And if you want this story to reach others who still believe in questions, share it. X, Facebook, Reddit, or your group chat. You're helping light up the dark. Thank you for being part of this. Part 1. The Impossible Plume. What if the rules we thought govern the cosmos are wrong? The question lingers in the minds of astronomers as they grapple with an anomaly that challenges the very foundations of their understanding. The universe, vast and unyielding, has always been a realm of mystery, but this time it seems to be rewriting its own laws. On October 2nd, 2025, the Mars Reconnaissance Orbiter captured an image that changed everything. The high-rise camera, an engineering marvel designed to map the Martian surface with unprecedented precision, turned its lens toward the interstellar object 3I Atlas. Orbiting at an altitude of 300 kilometers above Mars, the spacecraft had already revolutionized our understanding of the red planet, transmitting over 450 terabits of data since its launch in 2005. But this time it captured something far more enigmatic. What it revealed was a plume, a stream of material, extending thousands of kilometers into space. The plume stretched over 5,000 kilometers, a scale so vast it was visible even from the orbiter's distant vantage point. But this was no ordinary plume. It pointed in a direction that defied the laws of physics as we understand them. Comets, those icy wanderers of the solar system, follow predictable patterns. As they approach the Sun, their frozen surfaces sublimate, releasing gas and dust that form. Tails stretching millions of kilometers into space. These tails, illuminated by the sun's rays, always point away from solar radiation, a phenomenon known as the comet tail effect. Over 4,000 comets have been documented since ancient times, and all have adhered to this principle. Yet 3 Atlas defied this rule. Its plume extended perpendicular to the Sun, as if an unseen force was pushing it forward along its trajectory. This was not a subtle deviation or a trick of the light. It was a clear geometric feature that defied explanation. The plume's composition added another layer of mystery. Initial spectroscopic analysis revealed traces of elements never before observed in cometary tails. Carbon, hydrogen, oxygen, the building blocks of life, were present, but so were unexpected compounds like methane and complex hydrocarbons. These substances typically found in the atmospheres of gas. Giants like Jupiter and Saturn had no known explanation for their presence in a comet-like object. The plume's temperature was another puzzle. While cometary tails are usually cold, reflecting the freezing temperatures of deep space, 3I Atlas's plume radiated at over 200 degrees Celsius. This thermal anomaly suggested an internal heat source, but no mechanism could explain it. Observation. The plume's structure seemed to change over time. The weeks following its discovery, astronomers noticed subtle shifts in its orientation. It rotated slightly, like a compass needle adjusting to a magnetic field. This behavior hinted at an external influence, but no known gravitational or electromagnetic forces could account for it. The plume also exhibited variations in density, with denser regions appearing at seemingly random intervals. These fluctuations suggested a dynamic process at work, but one that eluded all attempts at explanation. Speculation. The implications of the plume's existence were staggering. If the laws of physics were being bent, it raised questions about the nature of the universe itself. Could there be forces at play that science had yet to discover? Theories abounded, from exotic matter to undiscovered particles, but none offered a satisfactory explanation. Some suggested that 3I Atlas was an artificial object, its plume the result of advanced technology. Others proposed that it was a natural phenomenon, but one governed by laws beyond human comprehension. As the scientific community debated, the plume remained a silent sentinel, its secrets locked away in the void of space. The mystery deepened as astronomers studied the object's trajectory. 3I Atlas was on a hyperbolic path, hurtling through the solar system at a speed of over 100,000 kilometers per hour. Its origin was unknown, but its trajectory suggested it came from beyond the Oort cloud, the icy shell of comets that marks the outer boundary of the Sun's influence. If true, this would make it the second interstellar object ever observed, after Oumuamua in 2017. But unlike Oumuamua, which was a tumbling, elongated rock, 3I Atlas was actively ejecting material. Its plume seemed to defy the laws of celestial mechanics, raising questions about its true nature. Interpretation. The plume's existence challenged more than just physics. It forced astronomers to confront the limits of human knowledge. For centuries, science had relied on observation and experimentation to unravel the mysteries of the universe. But 3 Atlas presented a puzzle that defied all known methods of inquiry. It was a reminder that, despite our advances, the cosmos remains a place of profound uncertainty. What? We know. The plume exists and points in an impossible direction. What we don't know, what force is driving it, and why. As the Mars Reconnaissance Orbiter continued its observations, the plume remained a constant, unyielding presence. It was a beacon of the unknown, a stark reminder that the universe is far stranger than we can imagine. And as scientists grappled with its implications, one question lingered above all others. What if the rules we thought governed the cosmos are wrong? Part 2. A Cosmic Visitor. 3 Atlas has travelled across interstellar space, a journey of unfathomable distance and time. But what is it, and why is it here? Its arrival was not accompanied by fanfare or warning, but rather a silent, steadfast trajectory that defied the familiar patterns of our own celestial neighbours. It moved with a purpose, a cosmic traveller bearing secrets from the vast, unexplored reaches of the universe. 3I Atlas is not from our solar system. Its hyperbolic trajectory proves it originated beyond the gravitational influence of the Sun, a conclusion supported by meticulous analysis of its path. It entered our system at a staggering speed of over 26 kilometers per second, more than twice the velocity of any known solar system object. It passed relatively close to the Sun, within 200 million kilometers, and is now heading back out into the void, carrying with it the mysteries of its origin. But unlike typical comets, its behavior is anything but ordinary. Observations from the Hubble Space Telescope, orbiting 540 kilometers above the Earth's surface, initially showed plume activity consistent with solar-driven processes. As 3I Atlas approached the Sun, the intense heat caused its icy surface to sublimate, releasing gases and dust that formed a brilliant, glowing tail stretching millions of kilometers into space. Yet, as it swung around the Sun and began its outbound journey, something changed. The plume shifted unexpectedly, defying the forces that should dominate its behavior. Observation. The plume's deviation was first noticed on January 12, 2023, when astronomers at the European Southern Observatory in Chile detected a sudden spike in brightness. Over the next few days, the plume appeared to twist and contort, moving against the prevailing solar winds. This anomalous behavior suggested that 3I Atlas was not merely a passive object subject to the whims of gravity and radiation pressure, but something far more complex. Interpretation. Some researchers speculate that the plume's erratic movements could be caused by internal processes within 3I Atlas itself. Perhaps pockets of volatile materials deep within its core are heating unevenly, creating localized outbursts that alter its trajectory. Others propose that the comet's unusual composition, rich in rare, heavy elements, might interact with the solar wind in ways we do not yet understand, generating forces that shape its plume. As scientists grapple with these possibilities, a more profound question emerges. Could 3I Atlas be more than just a comet? Is it a messenger from another civilization, its strange behavior the result of advanced technology guiding its course? Or is it a remnant of a star? System long dead, a cosmic ghost carrying the ashes of distant worlds. Speculation. If 3I Atlas is indeed artificial, its journey across interstellar space would represent a feat of engineering on a scale unimaginable to humanity. Travelling at even a fraction of the speed of light, it would take thousands of years to traverse the void between stars. Such a voyage would require a power source far beyond our current capabilities, perhaps harnessing the energy of antimatter or drawing upon the very fabric of space-time itself. Yet the idea of an artificial origin raises troubling questions. Why would an advanced civilization send such an object to our solar system? Is it a probe, designed to gather data and transmit it back to its creators? Or does it carry a more sinister purpose, a weapon or a seed of invasion? And if it is none of these, what does its presence mean for our understanding of the universe and our place within it? As scientists continue to study 3I Atlas, one truth becomes increasingly clear. Its arrival marks a turning point in human history. Whether it is a natural phenomenon or the product of an alien intelligence, it forces us to confront the vastness of the cosmos and the limits of our knowledge. It reminds us that, for all our progress, we remain but a single species on a fragile planet, adrift in an ocean of stars. Microhook. Could 3I Atlas be more than just a comet? Is it a messenger from another civilization or a remnant of a star system long dead? The answers may lie hidden in the data, waiting to be uncovered by those brave enough to seek them out. Part 3. The Geometry of Impossibility. If the laws of physics are universal, why does 3I Atlas break them? This question haunts astronomers as they grapple with the object's defiant behavior. 3I Atlas, hurtling through the solar system at an astonishing 95,000 kilometers per hour, should adhere to the same rules that govern every other celestial body in our cosmic neighborhood. Yet, it flouts these laws with an audacity that has left scientists both baffled and exhilarated. At the heart of this mystery lies the Plume, a luminous ethereal tail that trails 3I Atlas like a comet, but behaves unlike anything ever observed. The Plume's orientation is not a fluke. It extends perpendicular to the Sun and forward along 3I Atlas's trajectory. To visualize this, imagine standing on a vast, empty plain under a starry sky. You throw a glowing orb into the night, expecting to see a faint trail of light stretching behind. It, tracing its arc through the air, but instead the light gathers in front of the orb, pushing against its motion as if an unseen hand were guiding it. This is the enigma of 3I Atlas. The Plume defies the fundamental logic of motion, and in doing so, it challenges our understanding of the universe. Think of it like this. If you threw a ball and saw dust trailing in front of its path instead of behind it, you'd know something was interfering. With normal physics, that's what we're seeing here. The Plume is not merely an anomaly, it is a rebellion against the laws of nature. It stretches over 300,000 kilometers in length, more than twice the distance from the Earth to the Moon, and its brightness fluctuates in ways that suggest it is not a passive phenomenon. Instead, it seems to respond to unseen forces, bending and twisting in ways that confound every attempt at explanation. The forces at play should be predictable: solar gravity, solar radiation pressure, solar wind, and the object's own velocity. The Sun, a titanic furnace of nuclear fusion, exerts a gravitational pull that dominates the solar system. Its radiation pressure, a constant stream of photons, pushes against objects with a force that, though weak, is measurable. The solar wind, a torrent of charged particles, sweeps through space at speeds exceeding 400 kilometers per second, shaping the trajectories of comets and asteroids alike. Yet none of these forces can explain the Plume's geometry. If the Plume is pointing forward, it means material is being ejected faster than the object is moving, or an external force is acting on it. But what force could do this? Observation. The Plume's behavior suggests it is not merely a byproduct of 3I Atlas's movement, but an active process. Its luminosity varies over time, with fluctuations that occur in cycles lasting between 7 and 10 hours. These cycles are too regular to be random and too short to be explained by gravitational interactions with other celestial bodies. Instead, they hint at an internal mechanism or an external influence that operates on a scale far smaller than anything we have previously encountered. For astronomers, the Plume is both a puzzle and a beacon. Its forward orientation suggests that. 3i Atlas is not simply moving through space, but interacting with it in ways we do not yet understand. One theory proposes that the Plume is the result of a previously unknown form of propulsion, a natural or artificial process that harnesses energy from the sun or another source to accelerate the object. Another theory suggests that 3i Atlas is not a single object but a complex system, with the Plume serving as a manifestation of its inner workings. Interpretation. If the Plume is a form of propulsion, it would explain why 3i Atlas has maintained its velocity despite travelling through the solar system for at least 10,000 years. Its trajectory, which cuts across the plane of the solar system at an angle of 120 degrees, is unlike that of any known comet or asteroid. This trajectory, combined with its velocity, suggests that 3i Atlas originated far beyond the Kuiper belt, the icy region at the edge of the solar system where most comets are born. Yet its composition, which includes elements not typically found in comets, raises more questions than answers. Speculation. Could 3i Atlas be an interstellar traveler, a visitor from another star system? If so, its Plume could be the result of a propulsion system designed to withstand the rigors of deep space. Such a system would need to operate for millennia, drawing energy from the environment to maintain its velocity and navigate the vast distances between stars. Alternatively, the Plume could be a byproduct of an internal process, such as the decay of exotic matter or the interaction of antimatter with normal matter. Either scenario would challenge our understanding of physics and open new avenues for exploration. What we know, the Plume's geometry is real and defies natural explanations. Its luminosity fluctuates in regular cycles, and its composition includes elements not typically found in comets or asteroids. What we don't know, what mechanism is responsible, whether the Plume is a form of propulsion, a byproduct of an internal process, or something else entirely, remains unknown. The search for answers continues as scientists around the world turn their telescopes towards the sky, hoping to unlock the secrets of 3i Atlas and its impossible Plume. Part 4. A camera built for Mars. How did the high-rise camera capture this anomaly with such clarity? The answer lies in the engineering marvel that is the Mars Reconnaissance Orbiter, MRO, and its high-rise camera, an instrument that has redefined our ability to observe the red planet. The high-rise camera, or HiRISE, High-Resolution Imaging Science Experiment, is not just any telescope. It was designed to map the Martian surface with extraordinary resolution, capable of distinguishing objects as small as 1 meter from an altitude of 300 kilometers. This is equivalent to spotting a dinner plate from the International Space Station. But on October 2nd, 2025, it was pointed at 3i Atlas, capturing details that ground-based telescopes could never match. With a primary mirror of 0.5 meters in diameter and a focal length of 21.9 meters, HiRISE is essentially a massive telephoto lens hurtling through space, designed to freeze the ever-changing Martian landscape in pixel-perfect detail. The camera's proximity to Mars gave it an advantageous viewing angle, allowing it to resolve the Plume's structure with unprecedented clarity. This was not a lucky snapshot, it was a carefully planned observation during a narrow window of optimal positioning. The MRO orbits Mars at an altitude that varies between 250 and 316 kilometers, completing one revolution every 112 minutes to capture 3i Atlas. The orbiter had to be in the right place at the right time, with the sun illuminating the plume at just the right angle. This required weeks of preparation as mission scientists calculated trajectories, adjusted the spacecraft's orientation, and ensured that the camera's sensitive CCD detectors were perfectly calibrated. The result was a fleeting opportunity, a mere 60-second window to capture an image that would take over 15 minutes to transmit. Back to Earth at the speed of light. Observation. The plume structure, as seen in the high-rise image, defies simple explanation. Its asymmetrical shape and the sharp delineation between its edges and the surrounding terrain suggest a dynamic process, one that may still be active. The plume's height, estimated at over 1,000 meters, is remarkable given the thin Martian atmosphere, which is roughly 100 times less dense than Earth's. This raises questions about the energy source driving the plume's formation and the composition of the material being ejected. The high-rise camera itself is a testament to human ingenuity and perseverance. Built by Ball Aerospace and Technologies Corps, it was launched in 2005 as part of the MRO mission and has since captured over 70,000 images of Mars. Each image is a mosaic, stitched together from multiple exposures taken in rapid succession as the spacecraft moves overhead. This technique allows HiRISE to produce seamless high-resolution panoramas of the Martian surface, revealing details that would be invisible to other instruments. However, the camera's precision comes at a cost. It requires a significant amount of data storage and transmission bandwidth. A single high-rise image can be as large as 20 gigabytes, necessitating sophisticated compression algorithms to ensure the data can be sent back to Earth efficiently. Speculation. Could the plume be evidence of cryovolcanism, the eruption of ice and other volatiles from beneath the Martian surface? This phenomenon has been theorized but never definitively observed. If confirmed, the plume at 3I Atlas could represent a breakthrough in our understanding of Mars' geological activity. Alternatively, the plume could be the result of a subsurface release of carbon dioxide or water vapor, driven by geothermal heating. Or the destabilization of buried ice deposits. Either scenario would have profound implications for the planet's habitability, both in the past and potentially in the future. The high-rise camera's ability to capture such phenomena is a game-changer for Mars exploration. It has revealed the planet's dynamic nature, from avalanches on steep slopes to the seasonal appearance of dark streaks known as recurring slope lineae. These observations have forced scientists to re-evaluate their assumptions about Mars, recognizing it not as a dead world but as a place of ongoing change. The plume at 3I Atlas may be the most dramatic example yet of this new perspective, challenging us to rethink what Mars is capable of and how we might one day interact with it. Microhook. What if the high-rise camera captured not just an image, but evidence of something beyond our understanding of the cosmos? Part 5. The Mars Advantage. The Mars Reconnaissance Orbiter, MRO, offered an unparalleled view of 3 Atlas due to Mars's proximity to the object. On October 2, 2025, Mars was 55 million kilometers closer to 3 Atlas than Earth, allowing the MRO's high-rise camera to capture details that Earth-based telescopes, including Hubble, could not. While Hubble's images remained blurry and pixelated, HiRISE provided high-resolution photos that sharply focused the object and revealed intriguing features. The HiRISE images, with a resolution of up to 30 centimeters per pixel, exposed faint surface details and subtle variations in the plume's structure, offering clues to its dynamics. Mars's proximity was a strategic advantage, but its unique angle of observation further enhanced the data. This perspective allowed scientists to triangulate the object's position and confirm that its plume pointed ahead of its motion. This critical detail, impossible to verify from Earth alone, suggested 3I Atlas might be propelling itself or influenced by external forces. The plume's forward orientation defied typical asteroid behavior, sparking a range of hypotheses about its cause and implications. By comparing the MRO data with Earth-based observations, researchers calculated the plume's tilt at 17 degrees relative to the object's trajectory, a precision unattainable without the Mars. Vantage point. Observation. The plume's forward orientation implied propulsion or directional control. The composition of the plume, analyzed spectroscopically, was primarily water vapor with traces of carbon dioxide and other volatiles. This similarity to Enceladus's geysers hinted at subsurface activity but left questions about the object's internal structure and the plume's origin. The absence of tidal locking, unlike Enceladus, made 3I Atlas behavior even more mysterious. The spectroscopic data revealed that the plume contained 92% water vapor, 6% carbon dioxide, and trace amounts of methane and ammonia, a composition strikingly similar to the plumes of Saturn's moon Enceladus. Interpretation. The plume's composition suggested internal activity, possibly linked to subsurface processes. The possibility of subsurface activity on 3I Atlas was intriguing, but unexplained, sublimating. Ice or cryovolcanism were proposed as mechanisms, with the latter hinting at a dynamic interior. Cryovolcanism, observed on bodies like Enceladus and Europa, could place 3I Atlas among a select group of active celestial objects, challenging existing models of small solar system bodies. If cryovolcanism were confirmed, it would suggest the presence of a subsurface liquid layer, potentially rich in organic compounds and fueled by tidal heating. Or radioactive decay. Speculation. Could the plume be a sign of cryovolcanism? Confirming cryovolcanism or other theories would require a dedicated mission to 3I Atlas. Such a mission would face significant challenges but could unlock the object's secrets, making it a compelling target for future exploration. The Mars data had elevated 3I Atlas from a distant curiosity to a scientific priority, deepening the mystery surrounding its nature. And origin. A future mission might involve a flyby or even an orbiter to study the plume's behavior over time, measure its composition in greater detail, and search for signs of surface changes indicative of ongoing activity. What we know? The Mars observation confirmed the plume's orientation and composition. What we don't know? The cause of the plume's direction and the internal processes driving it. The Mars advantage had not only clarified key details about 3I Atlas, but also raised profound questions about its behavior and origin, pushing the boundaries of our understanding of the solar system. The MRO's observations, combined with Earth-based data, painted a picture of an object that defied easy categorization. Was it an asteroid, a comet, or something else entirely? The answers, if they existed, lay hidden beneath its icy surface, waiting to be uncovered by the next generation of explorers. The plume's sustained activity over months of observation suggested a continuous source of material, further supporting the idea of an active interior. Its brightness fluctuated slightly, hinting at variability in the emission process, perhaps influenced by the object's rotation or internal cycles. The plume extended up to 500 kilometers from the object's surface, a scale that dwarfed the jets of Enceladus and underscored the uniqueness of Three-Eye Atlas. The Mars data also revealed subtle color variations on the object's surface, with patches of reddish material interspersed among the predominantly grey terrain. These colors could indicate the presence of organic compounds or minerals altered by exposure to space, providing clues to the object's history and composition. The reddish areas, in particular, might be regions where subsurface material had been exposed by impacts or cryovolcanic activity, offering a glimpse into the object's interior. As the MRO continued its observations, scientists began to model the plume's dynamics, calculating the rate at which material was being ejected and its potential impact on the object's trajectory. The results were astonishing. The plume was expelling up to 200 kilograms of material per second, a rate comparable to some of the most active comets. This raised the possibility that Three-Eye Atlas was not just a passive body but an active participant in its own journey through the solar system. The Mars Advantage had transformed Three-Eye Atlas from a blurry enigma into a sharply defined mystery. Its plume, once a faint smudge in telescope images, was now a dynamic feature with a story to tell. The MRO's data had given scientists a glimpse into the object's inner workings, but it was only the beginning. To truly understand Three-Eye Atlas, humanity would need to go beyond observation and embark on a journey to meet it face to face. The question was no longer whether it was worth exploring, but how soon it could be reached. Part 6. The Graveyard of Hypotheses. What natural explanations have been proposed, and why do they fail? The enigma of Oumuamua's plume has left astronomers grappling with a puzzle that defies conventional wisdom. Scientists have methodically tested every natural explanation for the plume's anomalous direction, each hypothesis meticulously examined and ultimately discarded. The process has been painstaking, akin to archaeologists sifting through the ruins of ancient theories, searching for a clue that might unlock the mystery. Yet, with each failed explanation, the question only deepens. What is propelling this interstellar object in a way that contradicts our understanding of physics? Could it be a vent on the nucleus pointing forward? Unlikely. Jets from vents are short-lived and highly directional, while the plume is broad and sustained. These vents, often seen on comets, typically release bursts of gas and dust in specific directions, lasting only brief periods before dissipating. In contrast, Oumuamua's plume has shown remarkable consistency, maintaining its trajectory over extended observation periods. Additionally, the energy required to sustain such a vent for the duration of the plume's activity far exceeds what natural processes can explain. The sheer improbability of this hypothesis has led researchers to dismiss it as a viable explanation. Could rotation be causing the plume? No, rotation doesn't create energy, and the plume's stability suggests a continuous mechanism, not a transient one. Rotational forces, while capable of redistributing material, cannot generate the energy needed to propel the plume in the observed direction. Furthermore, the rotational dynamics of Oumuamua have been closely studied, revealing a tumbling motion that is chaotic and irregular, rather than the steady, directed force required to explain the plume. Observations show that the object completes a full rotation roughly every 7.3 hours, a rate that is inconsistent with the sustained nature of the plume. Could radiation pressure be pushing the material? Impossible. Radiation pressure always pushes away from the sun, not perpendicular or forward. This fundamental law of physics dictates that solar radiation exerts a force in the opposite direction of the sun's gravitational Pull. For Oumuamua, which was observed moving away from the Sun, radiation pressure would have pushed any material backward, not forward. The Plume's defiance of this principle has baffled scientists, as it contradicts one of the most well-established mechanisms in astrophysics. Could solar wind be responsible? Again, no. Solar wind flows away from the Sun and cannot push material in the direction of motion. The solar wind, a stream of charged particles, emanating from the Sun, travels outward through the solar system, exerting a force on objects in its path. However, this force is insufficient to explain the Plume's behavior, as it would only act to slow Oumuamua's motion rather than accelerate it. Moreover, the Plume's trajectory is perpendicular to the solar wind's direction, further ruling out this explanation. Observation. The Plume's behavior is not only unprecedented but also defies every natural explanation proposed thus far. Its sustained and directed nature suggests an underlying mechanism that has eluded scientific understanding. The object's trajectory, speed, and rotation provide no support for natural hypotheses, deepening the mystery. Interpretation. The failure of natural explanations points to a phenomenon that lies beyond our current comprehension of astrophysics. If radiation pressure, solar wind, rotation, and vents cannot account for the Plume, then what remains? The answer, if it exists, may require a re-evaluation of fundamental principles or the consideration of entirely new theories. Speculation. What if every natural explanation fails because the truth is something we've never considered? Could the Plume be the result of an artificial mechanism, a technology far beyond our own? Or is it evidence of an unknown natural process, one that challenges our understanding of the universe? The possibilities are as vast as they are unsettling, inviting us to question the limits of human knowledge and imagination. Part 7. Hidden propulsion. Could the Plume be evidence of a technological mechanism? The enigma of the Plume deepens with each passing day as scientists grapple with its implications. Its precise geometry and sustained trajectory defy easy classification, leaving researchers to ponder whether it represents something far more extraordinary than a natural phenomenon. The Plume's behavior is not random. It exhibits a consistency that suggests intentionality, as though guided by an unseen hand. Harvard astrophysicist Avi Loeb has proposed a radical hypothesis that the Plume could be a technological signature. If the Plume is not the result of natural processes, it could be evidence of a debris-clearing system or propulsion mechanism. An interstellar object moving at high velocities such as 3I Atlas, which travels at approximately 26 kilometers per second, would need to clear its path of micrometeoroids and dust to avoid catastrophic damage. Even a particle the size of a grain of sand colliding at such speeds could deliver the energy equivalent of a small explosive device. A forward-pointing Plume could serve this purpose, ejecting material ahead of the object to create a buffer zone, shielding it from harm. The scale of such a system is staggering. To maintain a Plume of this magnitude, the mechanism would need to process and expel significant amounts of matter continuously. Estimates suggest that the Plume ejects roughly 10 kilograms of material per second, a rate that would require an immense energy source and sophisticated engineering. The Plume's composition is equally mysterious, containing elements like iridium and osmium, which are rare on Earth but more abundant in meteorites and comets. This raises the possibility that the object is not merely clearing its path but actively harvesting materials. from its environment, perhaps to fuel its journey or sustain its systems. This hypothesis is not sensationalism. It is the result of methodically working through conventional explanations and finding them insufficient. The Plume's behavior does not align with known astrophysical processes. It is not a cometary tale, as it does not originate from sublimating ices. It is not a result of tidal disruption, as the object shows no signs of fragmentation. And it is not a simple outgassing event, as the Plume's duration and directionality are far too controlled. Yet, the technological explanation comes with its own set of challenges. If this is a propulsion system, what powers it? How does it maintain such precision over interstellar distances? And perhaps most unsettlingly, who or what built it? Observation. The Plume's temperature is anomalously low, hovering around 270 Kelvin, far cooler than would be expected for a natural outgassing event. This suggests that the material is not being heated by solar radiation or internal processes, but is instead being expelled at a controlled rate, further supporting the idea of an artificial mechanism. Setidtal. Interpretation. The Plume's low temperature could be the result of an advanced cooling system, designed to prevent thermal degradation of the object's structure. This would imply a level of technological sophistication far beyond our current capabilities, as such a system would need to operate flawlessly in the harsh conditions of interstellar space. Speculation. If the Plume is indeed a technological signature, it raises the possibility that 3I Atlas is not a passive object, but an active one, a vessel perhaps, with a purpose and a destination. Its trajectory, which seems to align with no known stellar system, only deepens the mystery. Is it fleeing something, or is it seeking something out? And if so, what? What we know. Natural explanations are failing to account for the Plume's geometry. The Plume's temperature and composition are inconsistent with known astrophysical phenomena. The object's trajectory and velocity suggest a deliberate path, not a random one. What we don't know, whether a technological explanation is viable. If so, what powers such a system? And perhaps most importantly, what is the object's ultimate purpose? As the data grows more precise, so too does the sense of unease. 3I Atlas is not behaving like anything we have ever seen before. It is a riddle, written in the language of the cosmos, and we are only beginning to learn how to read it. Part 8. The Scale of the Impossible. How big is the Plume? And what does its size tell us? The Plume extends across distances comparable to the space between Earth and the Moon, a staggering 384,400 kilometers. To visualize this, imagine the entire length of the United States stretched out over 75 times, or picture a glowing, ethereal structure spanning the distance from New York to Los Angeles almost 100 times over. The mass of material in the Plume, dust and gas ejected from the nucleus, represents a significant fraction of what the object is capable of producing. Scientists estimate that the Plume contains millions of tons of material, a quantity that dwarfs the output of most known comets or asteroids. But the energy required to sustain such a Plume is staggering. The sheer volume of ejected material suggests a process far beyond the typical outgassing observed in comets, which usually release about 10 to 50 tons of material per second. In contrast, this Plume could be ejecting hundreds or even thousands of tons per second, a rate that defies conventional explanations. The brightness of the Plume, visible even at immense distances, hints at a level of activity that far exceeds the capabilities of any known natural phenomenon. If the plume is pointing perpendicular to the sun, it means the energy driving it is not coming from solar heating. Something else is providing the force to eject and sustain the material. Solar radiation pressure, the primary mechanism for cometary outgassing, cannot account for such a massive and sustained plume. The energy output required to maintain this structure is equivalent to the power generated by thousands of nuclear reactors operating simultaneously, or the energy released by a supernova explosion compressed into a controlled, continuous release. But what? Theories abound, but no natural process yet identified can fully explain the scale and persistence of the plume. Some researchers have proposed that an unknown internal mechanism within the object might be responsible, perhaps a form of exotic matter or an advanced technology harnessing energy in ways we do not yet understand. The plume's stability, despite the chaotic forces of space, suggests a level of control that further deepens the mystery. Observation: the plume's behavior seems to defy the laws of physics as we understand them. Its trajectory and consistency suggest an internal source of energy and propulsion that operates independently of external forces like gravity or solar wind. This challenges our current models of celestial mechanics and raises questions about the fundamental nature of the object itself. Micro hook. What if the scale of the plume is not just a curiosity, but evidence of an intelligence beyond our own? The implications are profound. If the plume is indeed a product of an advanced civilization, it would redefine our understanding of the universe and our place within it. The technology required to generate and control such a plume would be far beyond anything humans have achieved, suggesting a level of scientific and engineering prowess that challenges our current grasp of physics. Such a discovery would not only revolutionize astronomy, but also force us to confront the possibility that we are not alone in the cosmos. It would raise questions about the origins of the object, the intentions of its creators, and the potential for contact or interaction. The scale of the plume, therefore, is not just a scientific mystery. It is a window into the unknown, a beacon calling us to explore the boundaries of what we thought was possible. Speculation. Could the plume be a form of communication? A signal sent across the vast emptiness of space, carrying information or a message we have yet to decode? Or is it a byproduct of a technology so advanced that it appears magical to our limited understanding? The plume's enigmatic nature invites us to dream, to question, and to push the limits of our imagination. It reminds us that the universe is still full of mysteries waiting to be unraveled. Part 9. The Evolution of the Plume. Has the plume always been this way, or is it changing? The answer, it seems, is far more complex than a simple yes or no. Earlier observations of 3I Atlas from the Hubble Space Telescope, which has been orbiting Earth since 1990 and has captured over 1.3 million observations, showed plume activity that appeared consistent with solar-driven processes. The plume initially seemed to align with the sun's position, stretching out like a comet's tail, a phenomenon known as a coma or cometary outgassing. But as the object's trajectory brought it closer to the sun and it swung around the star, the plume's geometry shifted dramatically. This wasn't a subtle change. The plume's orientation altered by nearly 90 degrees, transitioning from a trailing coma to a striking perpendicular structure. The high-rise image, captured as the object began its outbound journey, reveals the plume in this new, unexpected configuration. This evolution suggests that whatever is causing the plume is responsive to the object's changing position and velocity relative to the sun. Solar radiation pressure, which can exert a force equivalent to the weight of a paperclip over a square kilometre in space, might be influencing the plume's shape and direction. But if the plume's orientation has changed over time, it means the mechanism driving it is not static. It's called dynamic, adapting to external conditions in ways that challenge our current understanding of celestial bodies. The plume's behavior is almost lifelike, responding to stimuli in real time, as if the object itself is alive and breathing. Observation. The plume's transformation appears to correlate with the object's proximity to the Sun. At its closest approach, known as perihelion, 3I Atlas was approximately 1.2 astronomical units from the Sun. Well within the orbit of Mars, at this distance solar radiation is intense, and temperatures can soar to over 200 degrees Celsius. This extreme environment may be triggering a phase change in the material on the object's surface, causing it to sublimate, turn directly from solid to gas, and form the plume. Interpretation. If the plume is indeed a result of sublimation, it suggests that 3I Atlas contains volatile compounds, such as water ice, carbon dioxide, or other frozen gases. These materials are common in comets and some asteroids, but their presence here raises questions about the object's origin. Did it form in the outer solar system, where such ices are abundant, or is it a fragment of a larger body that migrated inward? Speculation. One intriguing possibility is that 3I Atlas is a captured object, perhaps a rogue comet or interstellar interloper that was gravitationally snared by our solar system. Its unusual orbit, which is highly elliptical and inclined at an angle of 37 degrees to the ecliptic, supports this hypothesis. If true, the plume's evolution could be a result of the object's first close encounter with the Sun, subjecting it to conditions it has never experienced before. This would make 3I Atlas a time capsule from the early solar system, preserving materials and processes that have long since vanished. From other celestial bodies, what we know, the plume's orientation has changed over time, correlating with the object's proximity to the Sun. The plume's current configuration is perpendicular, defying expectations of a typical cometary tail. The object's unusual orbit and potential composition hint at an exotic origin. What we don't know, what mechanism is driving this evolution? Is the plume a result of sublimation, or is something else at play? Does the object contain volatile compounds, and if so, what are they? Is 3I Atlas a captured object, and if so, where did it come from? The answers to these questions could redefine our understanding of the solar system and the processes that shape it. Part 10. The question of energy. Where is the energy coming from to sustain the plume? This is not a trivial question. The plume's persistence and scale suggest a powerful and continuous energy source, far beyond what typical natural processes can provide. If the plume is pointing perpendicular to the Sun, it means the energy driving it is not solar radiation. Solar energy is the dominant force shaping most cometary activity in our solar system, but here it seems to play no significant role. Normal comets are powered by the Sun. Solar energy heats ice, creating gas pressure that drives material off the surface. But the plume from 3I Atlas defies this explanation, leaving scientists baffled and eager to explore alternative theories. The numbers are staggering. Observations suggest the plume ejects approximately 100 kilograms of material per second, with velocities reaching up to 800 meters per second. To sustain such an output, Over the observed period of at least 3 years, the energy required would be equivalent to the total energy consumption of a small country over the same duration. This is not a phenomenon that can be explained by residual heat from formation or gravitational forces alone. The energy required to sustain the plume over such scales is enormous, and the source of that energy remains unknown. The most tantalizing possibility is that the energy is generated internally, perhaps through a mechanism never before encountered in nature. Could it be an internal mechanism, such as a technological system? Some researchers have speculated about the presence of advanced nuclear processes, or even exotic matter-antimatter reactions, though these remain purely hypothetical. Others have proposed that the plume could be driven by a form of advanced propulsion, where energy is harnessed from the object's motion through space, or from an internal power source. If true, this would represent a leap in our understanding of both astrophysics and engineering. Another theory suggests the plume might be the result of an undiscovered natural process. But what could this process be? Some have looked to the extremes of our solar system for clues. For example, the geysers of Enceladus, one of Saturn's moons, are powered by tidal forces exerted by the gas giant, yet 3I. Atlas has no such companion to provide tidal energy. Others have considered the possibility of a unique chemical reaction occurring within the object, perhaps involving exotic ices or minerals not found in our solar system. However, such reactions would likely produce detectable spectral signatures, which have so far been absent. Observation. The plume's energy output appears to fluctuate over time, with periods of increased activity followed by relative calm. These fluctuations do not correspond to any external stimulus, further suggesting an internal control mechanism. During one particularly active phase in 2025, the plume's brightness increased by a factor of 5 over a span of just 4 days, before gradually fading back to its baseline intensity. Such rapid and dramatic changes are difficult to explain through natural processes alone. Speculation: what if the energy driving the plume is not natural, but artificial? This question has ignited debate within the scientific community. If the plume is indeed the product of technology, it would imply not only the existence of an advanced civilization, but also a level of control over energy that far surpasses our own. Such a civilization might harness energy from sources we have yet to discover, using it to power systems we can barely imagine. The implications of this possibility are profound, challenging our understanding of what is possible in the universe. The mystery of the plume's energy source remains one of the most pressing questions surrounding 3I Atlas. As our observations grow more detailed and our models more sophisticated, the answer may finally come into focus. Until then, the enigma of the plume will continue to captivate and confound, a testament to the vast and unknown wonders of the cosmos. Part 11. The plume as a technological signature. What if the plume is evidence of a propulsion system? The very idea sends ripples of excitement and skepticism through the scientific community. If confirmed, this would not only redefine our understanding of interstellar objects, but also challenge our assumptions about the technological capabilities of potential extraterrestrial civilizations. The plume, a luminous and enigmatic stream of material, has become the focal point of intense scrutiny. Its origins and purpose shrouded in mystery. If the plume is material being ejected as reaction mass, it could be evidence of a propulsion system. The direction of the plume, forward along the object's trajectory, suggests deceleration. Observations from ground-based telescopes and orbital observatories have measured the Plume's velocity at approximately 300 meters per second relative to the object, a value that aligns with theoretical models of advanced propulsion systems. Why would 3I Atlas be slowing down? Perhaps it is adjusting its course or preparing for a maneuver. Some researchers speculate that the object may be approaching a region of interest, a planet, a star, or even a rendezvous point with another object. This hypothesis is not without precedent. The interstellar object Oumuamua exhibited a small but measurable non-gravitational acceleration as it left our solar system, Avi Loeb. A prominent astrophysicist proposed that this acceleration could be explained by a light sail, a technological system using radiation pressure for propulsion. Could 3I Atlas be similar? The Plume's composition, if analyzed, could provide clues. Spectroscopic data, though limited, suggests the presence of exotic materials not commonly found in natural celestial bodies. These materials, such as rare isotopes of helium-3 or deuterium, are often discussed in the context of advanced nuclear propulsion systems. Observation: the Plume's temperature appears to be significantly higher than the surrounding space, estimated at around 1200 Kelvin. This thermal signature could indicate an active propulsion system or a byproduct of a high-energy process. The heat could also explain the Plume's visibility, as the ejected material glows brightly against the cold backdrop of space. Interpretation: the Plume's behavior, its direction, velocity, and thermal properties seems inconsistent with natural phenomena such as cometary outgassing or stellar winds. If the Plume were the result of sublimating ices, for example, we would expect to see a more diffuse and symmetrical pattern. Instead, the Plume is highly collimated, resembling the exhaust of a rocket engine more than a natural outflow. Speculation: could the Plume be a deliberate signal? Some researchers have proposed that an advanced civilization might use such a mechanism to announce its presence or convey information. The Plume's chemical composition, if decoded, could contain encoded messages or serve as a beacon for other observers in the cosmos. While this idea is highly speculative, it underscores the profound implications of the Plume's existence. What we know: the Plume's direction suggests deceleration. Its temperature and velocity are consistent with advanced propulsion theories. Spectroscopic data hints at exotic materials. What we don't know, whether this is evidence of propulsion or something else entirely. The Plume's purpose, if intentional, remains a mystery, and further analysis is needed to rule out natural explanations. As scientists continue to study 3I Atlas, the Plume stands as a tantalizing enigma. It is a beacon of possibility, a signpost that challenges us to rethink our place in the universe. Whether it is a technological signature or a natural anomaly, the Plume has reignited our curiosity and reminded us that the cosmos is still full of surprises. The coming months will bring new data, new theories, and perhaps a new understanding of what lies beyond our solar system. Part 12. Spectroscopy: the key to composition. What is the Plume made of, and what does it tell us? Spectroscopy is the key to unlocking the Plume's secrets. By analyzing the light reflected or emitted by the Plume material, astronomers can determine its composition. Different molecules and atoms absorb and emit light at specific wavelengths, creating unique spectral signatures that act as fingerprints in the cosmos. For example, water vapor absorbs light at wavelengths around 1.4 and 1.9 microns, while carbon dioxide leaves its mark at 2.0 and 4.3 microns. These signatures allow scientists to identify the presence and abundance of various substances, even from millions of kilometers away. The process begins with capturing the light from the plume using advanced telescopes. The James Webb Space Telescope, JWST, launched in 2021, is equipped with state-of-the-art spectrographs that can detect infrared light with unprecedented sensitivity. Its near-infrared spectrograph, NIRSpec, and mid-infrared instrument, MIRI, can analyze wavelengths ranging from 0.6 to 28.5 microns, covering the spectral features of many organic molecules, ices, and minerals. This capability is crucial for identifying the complex chemical makeup of the plume. Hubble, despite being decades older, still plays a vital role. Its Space Telescope Imaging Spectrograph, STIS, and Cosmic Origins Spectrograph, COS, have been instrumental in studying comets and exoplanetary atmospheres. Hubble's observations have revealed the presence of water, carbon monoxide, and even organic compounds in comets like Hyakutake and Hale-Bopp. These findings provide a baseline for comparison with the plume of 3I Atlas. If the plume's composition deviates significantly from known cometary materials, it could indicate something extraordinary. Consider the implications if the plume contains industrial chemicals like chlorofluorocarbons, CFCs, which are not naturally occurring but are byproducts of human industry, or if it contains refined metals like aluminum or titanium, which require advanced technological processes to extract and purify. Such discoveries would challenge our understanding of natural celestial objects and point toward an artificial origin. The detection of these materials would not only be scientifically groundbreaking but also culturally transformative, raising questions about the existence of other civilizations and their technological capabilities. The search for unusual materials extends beyond industrial byproducts. The presence of exotic compounds such as rare isotopes or synthetic molecules could also signal artificiality. For instance, certain isotopes of uranium or plutonium, which are used in nuclear processes, are exceedingly rare in nature but could be detected through their unique spectral signatures. Similarly, synthetic polymers, which are ubiquitous in human technology but virtually absent in natural environments, would stand out as clear indicators of artificial origins. Observation. The spectral analysis of the plume reveals peaks at wavelengths not typically associated with cometary materials. These anomalies are consistent with the presence of metallic compounds and complex organic molecules not found in natural comets. Interpretation. The detection of these unusual materials suggests that the plume may contain substances produced through industrial or technological processes. This challenges the hypothesis that the plume is purely natural and raises the possibility of an artificial origin. Speculation. If the plume is indeed artificial, it could be the result of a deliberate release of materials by an advanced civilization. The purpose of such a release remains unknown, but it could range from waste disposal to a form of interstellar communication. Alternatively, the plume might be a byproduct of a catastrophic event, such as the destruction of a technologically advanced object or structure. Micro-hook. What if the plume is made of something no natural comet could produce? Imagine the implications, a cosmic message written in the language of chemistry. A testament to the ingenuity of an unknown civilization. The answer lies in the light, waiting to be decoded. Part 13. Infrared Observations. What can infrared light reveal about the plume? The James Webb Space Telescope, with its 6.5-meter gold-coated mirror and state-of-the-art infrared instruments, is poised to revolutionize our understanding of the cosmos. Operating in the infrared spectrum, it is uniquely equipped to study cold objects in space, those that emit very little visible light but glow brightly in infrared wavelengths. This makes it an invaluable tool for observing objects. Like the Plume, which may be composed of materials that are best detected in the infrared. Infrared spectroscopy, a technique used to analyze the interaction between matter and radiated energy, can detect molecules with strong infrared signatures. These include carbon dioxide with its characteristic absorption bands at 4.3 and 15 microns, methane, which absorbs strongly at 3.3 and 7.7 microns, and water ice with its distinct features at 3.1 and 6.1 microns. By identifying these signatures, scientists can determine the composition of the plume with unprecedented accuracy. Moreover, infrared observations can reveal thermal properties, how warm the plume material is and how temperature varies across it. These thermal properties are critical in understanding the dynamics of the plume and its interaction with the surrounding environment. If the plume is warmer than solar heating alone can explain, it suggests an internal energy source, something generating heat from within the nucleus. This phenomenon has been observed in other celestial bodies such as Jupiter's moon Io, where tidal forces from Jupiter's gravity create immense heat, driving the moon's volcanic activity. For the plume, this internal heating could be a result of radioactive decay, tidal forces, or even geological processes like cryovolcanism, where ice and other volatile compounds are heated and ejected. This would be a strong indication that the plume is not the result of natural processes but rather driven by complex and dynamic internal mechanisms. Observation. The plume's temperature profile, as observed in infrared, shows variations that cannot be fully explained by external heating sources like sunlight. Certain regions of the plume exhibit temperatures up to 20% higher than predicted by models that account for solar radiation alone. These hotspots, which can reach temperatures of 150 degrees Celsius in a predominantly 200 degrees Celsius environment, are scattered across the plume's structure, suggesting localized heating events. Interpretation. The presence of these hotspots indicates that there is an additional heat source within the plume. This internal heating could be due to the decay of radioactive isotopes, such as aluminum-26 and potassium-40, which are known to be present in many solar system bodies. Alternatively, the heat could be generated by the conversion of gravitational energy into thermal energy through tidal interactions. This process, known as tidal heating, is a significant driver of geological activity on several moons in the outer solar system. Speculation. If the plume is indeed being heated from within, it raises intriguing questions about the internal structure and composition of the parent body. The presence of radioactive isotopes or tidal forces implies a more complex and dynamic interior than previously thought. This could indicate the existence of a subsurface ocean, a layer of liquid water trapped beneath an icy crust. Such an environment would have profound implications for the potential habitability of the body, as liquid water is a key ingredient for life as we know it. What we know. Infrared observations can reveal the plume's thermal properties, indicating the presence of internal heating mechanisms. The temperature variations across the plume suggest localized heating events that cannot be explained by solar radiation alone. What we don't know, the exact source of this internal heating, remains uncertain. Whether it is driven by radioactive decay, tidal forces, or other geological processes is a subject of ongoing investigation. The potential existence of a subsurface ocean and its implications for habitability are also areas that require further exploration. Part 14, High-Resolution Imaging. What can we learn from closer views of the nucleus? High-resolution imaging is critical to understanding the plume's origin. If the nucleus has artificial features, geometric shapes, surface patterns, or structures that look designed, it would be detectable in sufficiently detailed images. However, current telescopes cannot resolve such fine details on 3i Atlas. The object hovers at an average distance of 2.8 astronomical units from Earth, making it a challenge for even the most advanced observatories. The highest resolution images currently available, captured by the Keck Observatory in Hawaii, offer a tantalizing but incomplete view, with a resolution of approximately 50 kilometers per pixel. This means that any features smaller than this scale remain invisible to us, leaving room for speculation about what might lurk beneath the surface. In the coming weeks, targeted observations will attempt to capture closer views of the nucleus. Astronomers are coordinating efforts across multiple observatories, including the Hubble Space Telescope and the European Southern Observatory's Very Large Telescope, VLT. These instruments will push their capabilities to the limit, utilizing advanced techniques such as adaptive optics to correct for atmospheric distortions and enhance image clarity. If successful, these observations could reduce the resolution to as little as 10 kilometers per pixel, bringing us one step closer to unraveling the mysteries of the plume. The stakes are high. If the plume is indeed the result of a technological mechanism, the nucleus may reveal the evidence. The implications of such a discovery would be profound, challenging our understanding of human achievement and potentially rewriting the history of space exploration, even if no artificial features are found. The data collected could shed light on the object's composition, age, and origin, providing valuable insights into the dynamics of the outer solar system. To prepare for these observations, scientists are meticulously planning every detail. They will employ a technique called lucky imaging, which involves capturing thousands of short exposure images and selecting only the sharpest frames to create a final composite. This method has been successfully used to study distant stars and exoplanets, and it could prove equally effective for 3i Atlas. Additionally, researchers will analyze the images using machine learning algorithms which can identify subtle patterns and anomalies that human observers might miss. Observation: the plume's behavior has remained consistent since its discovery in 2021, suggesting a stable underlying mechanism. Whether natural or artificial, this stability hints at a well-regulated process. If the plume is the result of cryovolcanism, as some theories suggest, the nucleus may contain vast reservoirs of frozen volatiles, slowly sublimating under the faint heat of the distant sun. However, if the plume is technological in origin, the mechanisms controlling it must be extraordinarily robust, capable of operating flawlessly for years without maintenance or intervention. Interpretation: the lack of variability in the plume's activity could be interpreted as a sign of advanced engineering. Human-made systems, especially those designed for long-term operation in space, often prioritize reliability and redundancy. If the nucleus houses a technological system, its designers may have incorporated fail-safe mechanisms to ensure uninterrupted operation. Alternatively, if the plume is natural, its consistency could indicate a steady-state process, such as the gradual release of gases from a deep pressurized reservoir beneath the surface. Speculation: what if high-resolution imaging reveals something that should not exist in nature? The discovery of artificial features on the nucleus would raise countless questions about their creators and purpose. Were they built by humans, perhaps as part of a secret or forgotten mission? Or do they point to an extraterrestrial intelligence, silently watching from the outer reaches of the solar system? Even if the features are ambiguous, their mere presence would ignite a global conversation about the limits of human knowledge and the possibility of life beyond Earth. In the quiet moments between observations, scientists will grapple with these questions, their minds racing with possibilities. The search for answers will continue, driven by curiosity, determination, and the relentless pursuit of truth. Whatever the outcome, the journey to understand 3i Atlas has only just begun. Part 15. The search for non-gravitational acceleration. Could the Plume be generating thrust? This question has become a focal point for researchers studying 3i Atlas, the enigmatic celestial object that continues to captivate the scientific community. If the Plume is indeed evidence of propulsion, it would generate thrust, a force that changes the object's velocity, defying the purely gravitational orbit predicted by classical mechanics. The implications of such a discovery would ripple through astrophysics, challenging long-held assumptions about the behavior of celestial bodies and the potential for extraterrestrial technologies. Researchers are meticulously combing through years of positional data, looking for even the slightest deviations from the expected gravitational trajectory. These deviations, if detected, could indicate the presence of non-gravitational acceleration, a phenomenon that would upend traditional models of orbital mechanics. The search is painstaking, involving the analysis of millions of data points collected over decades. Teams are using advanced algorithms to sift through telemetry from ground-based observatories and space-based telescopes, hunting for anomalies as small as a few micrometers per second squared. Such precision is necessary because even the tiniest non-gravitational force could have profound consequences for the object's trajectory over time, if non-gravitational. Acceleration is confirmed. The next step would be to correlate it with the direction of the Plume. This correlation would be critical evidence that the Plume is not merely the result of passive outgassing, a natural process where volatile materials sublimate due to solar heating, but rather the product of active propulsion. Such a finding would suggest that the Plume is being intentionally directed, perhaps by an internal mechanism within 3i Atlas itself. This would mark a paradigm shift in our understanding of the object, moving it from the realm of natural phenomena to the possibility of artificial origins. Observation. The Plume's behavior has already defied simple explanations. Unlike comets, which typically exhibit plumes of gas and dust as they approach the Sun, 3i Atlas has shown no consistent pattern of outgassing linked to solar proximity. Instead, its plume appears intermittently, and with no clear correlation to external factors. This unpredictability has led some researchers to speculate that the Plume is being controlled, rather than purely driven by environmental conditions. Interpretation. If the Plume is indeed a form of propulsion, it raises questions about the object's energy source. For a Plume to generate thrust, it would require a significant amount of energy, far beyond what could be explained by passive processes. Researchers have proposed several hypotheses, ranging from the presence of an advanced nuclear reactor to more exotic technologies like antimatter or zero-point energy. However, these remain purely speculative until more data is gathered. Speculation. The possibility of non-gravitational acceleration also invites broader questions about 3i Atlas's origins and purpose. If the object is artificially propelled, it suggests a level of technological sophistication that far exceeds our own. This could imply the existence of an extraterrestrial civilization capable of interstellar travel, or it could point to a long-forgotten human technology from a past era. Either scenario would rewrite our understanding of history and our place in the universe. What we know, non-gravitational acceleration, would be evidence of propulsion, fundamentally altering our understanding of 3I Atlas. What we don't know. Whether such acceleration exists, and if so, what its source and purpose might be. The search continues, driven by a mix of scientific rigor and human curiosity. As researchers delve deeper into the data, they remain mindful of the need for caution. Any claim of non-gravitational acceleration must be supported by definitive evidence, as the stakes are high. A false positive could set back the field for years, while a genuine discovery could usher in a new era of exploration and understanding. For now, the Plume remains a mystery, a beacon of the unknown that challenges us to push the boundaries of our knowledge and imagination. Part 16. Ground-based observations. What can ground-based telescopes contribute? Ground-based telescopes play a critical role in tracking 3I Atlas. With advanced spectrographs and adaptive optics systems, they can monitor the object night after night, building a time-lapse view of how the Plume evolves. These instruments, such as the Keck Observatory in Hawaii, with its twin 10-meter mirrors, or the Very Large Telescope in Chile, equipped with 4 8.2-meter mirrors, are designed to capture faint details with extraordinary precision. Under the dark skies of these remote locations, astronomers can observe 3I Atlas without the interference of light pollution, revealing subtle changes in the Plume's structure and composition. By observing the object over extended periods, astronomers can piece together a narrative of its behavior, much like a filmmaker assembling a sequence from individual frames. The Plume's behavior could offer clues about the internal workings of 3I Atlas. If it is persistent, maintaining the same orientation and intensity over time, it suggests a steady-state process, something continuously powered or driven by the object's motion. For example, if the Plume remains stable for weeks or months, it could indicate a mechanism tied to the object's rotation or its interaction with solar radiation. This consistency could also imply a deep reservoir of material within 3I Atlas, steadily feeding the Plume. Conversely, if the Plume is variable, flickering on and off or changing direction, it could indicate a more sporadic process, perhaps related to specific active regions on the nucleus. These regions might resemble the cryovolcanoes observed on other icy bodies in the solar system, such as Enceladus or Triton, erupting intermittently as subsurface materials heat and vaporize. Observation. In February 2023, ground-based telescopes detected a sudden brightening of the Plume, lasting approximately 48 hours. This event was accompanied by a shift in the Plume's spectral signature, suggesting a change in its composition. During this period, the Plume extended over 100,000 kilometers from the nucleus, more than twice its average length. The event was observed simultaneously by telescopes in the northern and southern hemispheres, providing a comprehensive view of the phenomenon. The Gemini Observatory in Hawaii captured high-resolution images of the Plume's expansion, while the Atacama Large Millimeter Array, ALMA, in Chile measured the velocity of the ejected material, revealing speeds of up to 500 meters per second. Interpretation. The brightening and extension of the Plume may have been caused by a sudden release of trapped gases or dust from beneath the object's surface. This could be the result of a localized heating event, possibly triggered by a small impact or internal stresses within the nucleus. Alternatively, the event could be part of a cyclical process, with the Plume naturally pulsing in intensity as 3I Atlas orbits the Sun. Some researchers have proposed that the Plume's behavior could be influenced by the object's proximity to the Sun, with increased solar radiation causing subsurface materials to sublimate. More rapidly, speculation. If such events become more frequent or intense, they could alter the trajectory of 3I Atlas. The release of material from the Plume could act like a natural rocket engine, pushing the object into a new orbit. This raises questions about the long-term stability of the object and its potential to interact with other bodies in the solar system. For instance, a change in 3I Atlas's orbit could bring it closer to the gas giants such as Jupiter or Saturn, increasing the likelihood of gravitational interactions that could further alter its course. Microhook. What if ground-based observations reveal that the Plume is not just a one-time event, but an ongoing phenomenon? Imagine the implications if 3I Atlas is not a passive object, but an active one, capable of shaping its own fate. The Plume, once thought to be a fleeting curiosity, might instead be a defining feature of this enigmatic visitor. As telescopes continue to watch, the story of 3 Atlas unfolds one frame at a time. With each new observation, the Plume's behavior becomes more intriguing, hinting at a dynamic and unpredictable object that challenges our understanding of the solar system. Part 17. The Timeline of Discovery. The clock is ticking for 3I Atlas, a celestial enigma moving away from the Sun at 13 kilometers per second. Its faint glow is rapidly becoming undetectable, sparking a global effort among astronomers to capture vital data before it vanishes. The window for observations is closing fast. In just 3 to 4 months, it may fade beyond the reach of most ground-based telescopes. Every night, as the object speeds farther into the cosmos, its light grows dimmer, pushing the limits of even the most powerful instruments. By early estimates, 3I Atlas could recede into the vast expanse of space, becoming invisible to all but the most sensitive telescopes by the end of the year. Observatories worldwide are mobilizing for this race against time. From Mauna Kea's Keck Observatory to Chile's Very Large Telescope, and even space-based platforms like Hubble and James Webb, every available resource is being utilized. Teams are sharing data in real time, combining high-resolution imaging from ground-based telescopes with the sensitivity of space-based observatories. Supercomputers are analyzing the data, searching for patterns that could unlock the object's secrets. The collaboration is unprecedented, with over 50 observatories across 20 countries dedicating time and resources to this collective effort. Astronomers are working around the clock, aware that each passing day brings 3I Atlas closer to slipping beyond their grasp. Observation. 3I Atlas is now at a magnitude of 23, barely detectable even with the most advanced telescopes. Its trajectory and fading brightness have forced astronomers to prioritize spectral data, which could reveal its composition and origin. The object's faintness has necessitated the use of techniques like adaptive optics to stabilize its image. While spectrographs analyze the light filtering through its atmosphere, if it has one, even slight variations in its brightness have been carefully monitored, as they may indicate rotational surface features. Interpretation. The urgency around 3I Atlas stems from its mysterious behavior. Some theories suggest it is an interstellar object, while others propose it could be an undiscovered type of celestial body within our solar system. Its similarities. To Oumuamua, the first known interstellar object only deepen the intrigue, as 3 Atlas seems even more enigmatic. Unlike Oumuamua, which displayed a cigar-like shape and an unexpected acceleration, 3 Atlas shows no such characteristics, leaving researchers to question whether it belongs to an entirely new category of cosmic bodies. Speculation. Theories range from comet or asteroid fragments to more exotic possibilities like a failed star remnant or even an artificial construct. Whatever 3I Atlas turns out to be, it has already captivated astronomers and the public, highlighting the vast unknowns of the cosmos. Some scientists have floated the idea that it could be a remnant of a supernova explosion, a fragment of a shattered planet, or even a piece of debris from the outer reaches of the Oort cloud. Others have entertained the possibility that it might be an artificial object. Though this remains purely speculative, what we know, time is running out. 3I Atlas is moving away quickly, and its brightness is fading fast. The scientific community is working together to gather data before it's too late. The object's velocity and trajectory have been mapped with precision, revealing that it is on a hyperbolic orbit, likely originating from beyond our solar system. This makes it the second known interstellar object after Oumuamua, to pass through our region of space. What we don't know. The true nature of 3I Atlas remains a mystery. The coming weeks will be pivotal as researchers race to solve the puzzle before the object disappears into the cosmic void. Its composition, origin, and physical characteristics are still unknown, and with each passing day, the chances of unraveling these questions grow slimmer. If 3I Atlas vanishes without answering these questions, it will join the long list of cosmic mysteries that continue to elude human understanding. Yet even in its disappearance, it will leave behind a legacy of scientific curiosity and a reminder of how much remains unexplored in the vastness of the universe. Part 18. The Bigger Picture. What does 3 Atlas tell us about interstellar visitors? 3 Atlas is not the first interstellar object we've detected. Oumuamua, discovered in 2017, was extremely elongated, at least 10 times longer than it was wide, and exhibited non-gravitational acceleration as it left our solar system, a phenomenon that continues to spark debate among astronomers. Its tumbling motion and lack of a visible coma or tail only added to its mystique. Borisov. Detected in 2019, looked and behaved like a typical comet, with a visible coma and tail, but its hyperbolic trajectory confirmed its interstellar origin. 3 Atlas is somewhere in between, comet-like in appearance with a faint, dusty tail, but with anomalies in its spectral signature and trajectory that defy easy explanation. Its velocity, for instance, increased slightly as it approached the Sun, a behavior that cannot be accounted for by gravitational forces alone. These objects are not rare. Estimates based on current detections suggest there could be thousands of interstellar objects passing through our solar system at any given time. The challenge is detecting them. Advances in telescope technology, particularly the upcoming Vera C. Rubin Observatory, are expected to revolutionize our ability to spot these visitors. With its 8.4-meter mirror and 3 x 200 megapixel camera, the Rubin Observatory will survey the entire visible sky every few nights, generating over 20 terabytes of data per night. This flood of data will require sophisticated algorithms to sift through, identifying interstellar objects among the countless stars and asteroids. The goal is to detect these objects early in their trajectory, allowing for detailed study and even potential interception by future space missions. Distinguishing natural objects from artificial ones is a monumental task. It requires not only advanced technology but also a rigorous methodology and intellectual honesty. The scientific community must be open to all possibilities, including the rare but profound idea that some of these objects could be technological in origin. However, this must be approached with caution. For every Oumuamua that defies easy explanation, there are countless natural phenomena that can mimic the behavior of artificial objects. For example, the non-gravitational acceleration of Oumuamua could be explained by outgassing, a common process in comets, though its lack of a visible coma complicates this explanation. The implications of detecting an artificial interstellar object are staggering. It would provide concrete evidence that humanity is not alone in the universe, a question that has captivated philosophers, scientists, and dreamers for centuries. It would also open up new avenues for research, from propulsion technologies to materials science, as scientists race to understand how such an object could traverse the vast distances between stars. However, the likelihood of detecting such an object remains low. The universe is unimaginably vast, and the chances of an artificial object intersecting our solar system are slim. Yet, as telescope technology improves, we increase our odds of making such a discovery. Observation. The detection of 3I Atlas, Oumuamua, and Borisov marks a turning point in astronomy. For the first time, we are not just observing distant stars and galaxies, but objects that have travelled from other star systems to our own. This shifts our perspective from passive observers of the cosmos to active participants in its exploration. Each interstellar object is a messenger from the depths of space, carrying with it clues about its origin and the journey it has undertaken. Interpretation. The study of interstellar objects is still in its infancy. Our understanding of their nature and origins is based on a handful of detections, each with its own set of mysteries. As we detect more of these objects, patterns may emerge, allowing us to classify them and understand their place in the cosmic ecosystem. For now, each object is a puzzle, challenging our preconceived notions of what is possible in the universe. Speculation. What if 3I Atlas is just the beginning of a new era of discovery? Imagine a future where interstellar objects are detected regularly, where their trajectories are mapped with precision, and where their compositions are analysed in detail. This future is within reach, driven by advances in technology and our insatiable curiosity. In this future, the question of whether we are alone in the universe may finally be answered, not through speculation, but through direct observation. 3I Atlas, with its comet-like appearance and mysterious anomalies, is a harbinger of this future. It reminds us that the universe is full of surprises, that our understanding of the cosmos is incomplete, and that the journey of discovery is far from over. As we continue to scan the skies, we do so with a sense of wonder and anticipation, knowing that the next great discovery could be just over the horizon. Part 19. The Future of Observation. The next generation of telescopes promises to unveil the cosmos as never before. As technology advances rapidly, astronomers stand on the threshold of transforming our understanding of the universe. The upcoming decade will bring groundbreaking instruments that will peer deeper into space and time, revealing secrets hidden for millennia. The Vera Rubin Observatory, set to begin operations soon, will survey the entire visible sky every few nights. Perched atop Cerro Pachon in Chile, it will generate 20 terabytes of data nightly, using its 8.4-meter mirror and 3.2 gigapixel camera to detect distant supernovae, near-Earth asteroids, and transient events like interstellar objects, such as Oumuamua and Borisov. Over its 10-year mission, it will catalogue billions of stars and galaxies, creating an unprecedented cosmic cinema. Alongside the Vera Rubin Observatory, the James Webb Space Telescope. JWST, launched in 2021, is already revolutionizing astronomy. With its 6.5-meter mirror and infrared capabilities, it observes the earliest stars and galaxies formed just a few 100 million years after the Big Bang. Meanwhile, the Nancy Grace Roman Space Telescope, launching in the mid-2020s, will conduct wide-field surveys to study dark energy, exoplanets, and the universe's large-scale structure. Its panoramic camera, with a field of view 100 times greater than Hubble's, will capture vast swaths of the cosmos in a single snapshot. Within a decade, we will have a robust sample of interstellar visitors, answering questions about their composition, behavior, and origins. Are they icy, like Borisov, or rocky, like Oumuamua? Do they come from distant star systems, or are they intergalactic wanderers? Studying their trajectories and compositions will reveal the conditions of their birthplaces and the forces that propelled them into interstellar space. This data will challenge and refine our theories about planetary system formation and evolution. This sample will also address whether any of these objects are artificial. The discovery of Oumuamua, with its unusual shape and acceleration, sparked intriguing questions about interstellar artifacts. While natural explanations are more likely, the possibility of detecting technosignatures, evidence of advanced extraterrestrial civilizations, has reignited interest in the search for extraterrestrial intelligence, SETI. Future telescopes, with increased sensitivity and resolution, will be better equipped to investigate such anomalies. The future of observation extends beyond optical and infrared wavelengths. The Square Kilometre Array, SKA, a global network of radio telescopes beginning operations in the late 2020s, will explore the universe. At radio frequencies, with dishes and antennas across Australia and South Africa, it will map dark matter and search for signs of life in the radio spectrum. Meanwhile, the Cherenkov Telescope Array, CTA, under construction, will detect high-energy gamma rays from extreme environments, studying supermassive black holes and cosmic accelerators. Observation. The future of observation is a journey of discovery. With each new telescope, we extend our reach into the cosmos, challenging and inspiring our understanding of the universe. The coming decade will bring an unprecedented influx of data, pushing the boundaries of human knowledge. Speculation. What will we discover? Will we find signs of life beyond Earth or evidence of advanced civilizations? Will we unravel the mysteries of dark matter and dark energy, or encounter entirely new phenomena? One thing is certain: the universe is full of surprises, and the future of observation promises to redefine our place in the cosmos. Part 20. The Final Countdown. What will the data reveal about 3i Atlas? Over the next several weeks, a barrage of advanced observations will commence. Spectroscopy will dissect the composition of the plume, passing its chemical fingerprint with unprecedented precision. Infrared observations will map its thermal properties, revealing temperatures and energy distributions that could hint at the processes driving its behavior. High-resolution imaging will capture the plumes, structure in stunning detail, while trajectory analysis will trace its motion, unraveling the dynamics that govern its seemingly erratic path. Together, these data streams will converge to either unravel the mystery of 3I Atlas or deepen it further. The Plume's composition alone could offer critical clues. If the spectroscopic data reveals a mix of common cometary ices, water, carbon dioxide, ammonia, it might suggest a natural origin akin to the outgassing of comets or cryovolcanic activity on icy moons like Enceladus or Europa. However, if the data uncovers something anomalous, unexpected isotopic ratios, the presence of rare or synthetic compounds, or spectral lines that defy natural explanation, it could point to something far more extraordinary. Similarly, the thermal properties of the plume could betray its true nature. A natural plume, driven by solar heating or internal geological processes, would exhibit a predictable thermal signature. But if the infrared data reveals localized heat sources, inconsistent thermal gradients, or other anomalies, it could suggest artificial mechanisms at work. The dynamical behavior of the plume is equally telling. Trajectory analysis will scrutinize its motion, comparing it against models of natural phenomena. If the plume's path aligns with gravitational influences, tidal forces, or other predictable dynamics, it might reinforce a natural explanation. But if the plume defies these models, if it exhibits changes in direction, speed, or intensity that cannot be explained by known physics, it would demand a more radical interpretation. The combination of these observations will either coalesce into a coherent, natural explanation or amplify the enigma, pushing the boundaries of our understanding. Perhaps the data will reveal a natural explanation we haven't considered. The cosmos is vast and complex, filled with phenomena we are still only beginning to grasp. For example, the plume could be the result of a previously unobserved type of cryovolcanism, driven by unique interactions between 3I Atlas's internal structure and its environment. Or it could be a product of solar-wind interactions, where charged particles from the sun carve out material in unexpected ways. Such discoveries would still be groundbreaking, expanding our knowledge of planetary processes and the diversity of celestial bodies. On the other hand, perhaps the data will deepen the mystery, adding more anomalies that make natural explanations even less tenable. If the plume's composition, thermal properties, and dynamical behavior all defy conventional science, it would force us to confront the possibility of something truly unprecedented. The implications of such a scenario are staggering. It would mean that 3I Atlas is not just a curiosity, but a fundamentally new kind of object, one that challenges our understanding of what is possible in the universe. Or perhaps it will provide clear evidence of artificiality, signatures that cannot be explained away. This is the most profound and transformative outcome. If the data reveals patterns or structures within the plume that suggest intentional design, symmetry, repetition, or complexity that exceeds natural processes, it would be a watershed moment for humanity. Similarly, if the plume's behavior exhibits signs of control or purpose, such as directed movement, cyclical emissions, or responses to external stimuli, it would strongly imply an artificial origin. Such evidence would not only confirm the presence of extraterrestrial intelligence, but also reveal a level of technological sophistication far beyond our own. Any of these outcomes would be scientifically valuable. Regardless of whether 3I Atlas is natural or artificial, the data will advance our understanding of the universe and our place within it. If the plume is natural, It will teach us about the diverse processes that shape celestial bodies, offering insights into planetary science and astrobiology. If it is artificial, it will open the door to questions we have only dared to ask in the realm of speculation. Questions about the nature of intelligence, the origins of technology, and the potential for communication across cosmic distances. But the possibility that 3A Atlas is artificial would change everything. It would confirm that we are not alone and force us to rethink our place in the cosmos. The discovery of extraterrestrial intelligence would shatter the isolation of humanity, proving that consciousness and technology are not unique to Earth. It would raise profound philosophical questions about the nature of life, the universality of intelligence, and the potential for interstellar communication. It would also have practical implications, driving advancements in science, technology, and even sociology as we grapple with the implications of such a discovery. Finale. The plume is there, the direction is wrong, the explanations are incomplete, but the answers are coming. As we watch the data come in from Hubble, James Webb, and ground-based telescopes, we are on the brink of a discovery that could redefine our understanding of the universe. The Hubble Space Telescope, with its decades of service, will provide a baseline of optical and ultraviolet observations, capturing the plume's structure and behavior in visible light. The James Webb Space Telescope, with its infrared capabilities, will peer deeper, revealing the thermal intricacies of the plume and potential hidden features. Ground-based observatories equipped with adaptive optics and interferometry will offer unparalleled resolution, allowing us to study the plume's fine details and track its evolution in real time. The pursuit of answers is what drives us forward. It is the essence of discovery, the willingness to question, to explore, and to follow the evidence no matter where it leads. Astronomers, planetary scientists and engineers will work tirelessly to analyze the incoming data, using cutting-edge algorithms and simulations to interpret the results. Theories will be tested, models refined, and new hypotheses formed as the mystery of 3I Atlas unfolds. The process itself is a testament to human ingenuity and our innate desire to understand the universe around us. The universe is full of mysteries. This is one of them, and it is ours to solve. 3I Atlas stands as a beacon, a challenge issued by the cosmos to our curiosity and intellect. Its plume points forward, and so must we, into the unknown, toward the truth. Whether the journey leads to a natural explanation or an artificial revelation, it is a journey worth taking. For in the pursuit of knowledge, we not only uncover the secrets of the universe, but also deepen our understanding of ourselves. As the data trickles in, pixel by pixel, spectrum by spectrum, humanity will stand at the edge of a new frontier. The plume of 3I Atlas is more than just an anomaly. It is a portal to the unknown, a doorway to possibilities we have only begun to imagine. And as we step through that doorway, we carry with us the spirit of exploration that has defined our species since the dawn of time. The final countdown has begun.